Okay. Yeah, so we actually have another result about the free energy, but this is more of a statistical or information theoretic question, or maybe combinatorial. So here's a picture. So the idea is I have a very large graph, and it's so large, I don't want to access it directly. So instead, I'm going to take a very small sample from it, and I'm going to hope that by sampling a small portion of the graph, so this is actually a weighted graph, right? So the edge weights are the GIJs. But I'll sample a very small portion of the graph, and I'm going to hope that just the information in this little random subgraph is going to be enough to actually compute the free energy of the original big Ising model. So that's the setup. And okay, so what do I mean by very large? Well, actually, I mean infinite. So there's this thing that's called a graphon, which is just sort of the infinite scaling limit of a dense graph. So this is a picture of the graphon if you take stochastic block models and sort of take their scaling limit. You'll get something like this, which is supposed to be sort of you can think of it as this is just the asymptotic adjacency matrix. Okay, so these are infinite size graphs, and we would like to compute their free energy. And graphons, like another reason to care about them, like as the picture suggests, they're a model for random graphs, which is better than GMP in that it can model non-homogeneous structure. So all GMPs look the same, but with graphons, we can get genuinely different graphs. Okay. So now I have a slide, which is just to define the notation. So we'll have n vertices in our Ising model, and then we'll take a sample of size q. And the important thing here is when I look at my small Ising model, I really need to rescale the weights. So I'm going to let jq be n over q times j, and that's because you basically want to preserve the total weight coming into each vertex. So if I kill many of the edges, I need to rescale the weights. And then you could just kind of hope that if I compute the free energy on the very little graph, then I rescale it by the appropriate n over q term, then I could hope that this is actually going to be a good estimate for the big free energy. And so that's the question we want to study. Is this a good estimator? And then if it was not a good estimator, maybe we could study other estimators that, we could try to find things that are better information theoretically. But usually this is a good estimator. And I should say that it's not just like we're inventing this kind of problem by ourselves, but actually there's a huge literature on property testing in dense graphs. So in particular, people are very interested in this problem of testing triangle freeness. So you want to see if a graph is close to triangle free or not. And basically the upper bounds for this are of tower type, and the lower bounds are quasi-polynomial. So there's this huge gap. And actually this is like one of the most, I think, important problems in combinatorics right now. Okay. So I just have one more slide on the notation. So okay, I mean this problem I wrote is studied by Alone et al. But actually there's many people who studied that problem for max cut. But basically, you want to you're given epsilon and you want to know how many samples do I need to take to get within like a 99% chance of correctness, and get within for max cut epsilon n squared, or for free energy epsilon n of the true answer. And I should say, why am I talking about max cut? It's a special case of the problem when you take an anti-ferromagnetic Ising model with very large edge weights. Okay, so for max cut, actually it's been known for a while, since like 2004, that you can actually get away with a 1 over epsilon to the 4th sample size. And actually, maybe surprisingly, this actually works for general max RCSPs for any fixed R without changing the exponent on epsilon. Okay, and for Ising models, unfortunately, we didn't know that much. So the best result was again in the graph limits literature, where they showed 2 to the 1 over epsilon squared bound. It actually would have been very interesting if this bound was tight, because it matches the runtime of our algorithms. So it would have given a very good explanation for why our algorithms run in time 2 to the 1 over epsilon squared, but it's not tight. So actually we can improve it to a polynomial on 1 over epsilon. And we have some lower bound, which actually also covers non-uniform sampling schemes, which shows you cannot do better than sort of poly 1 over epsilon. Okay? And we actually show a more general result, which looks like this. So you can see, it's some function of jf in j infinity. And the thing that's important about this is this gracefully works even in the regime where my graph is not truly dense. So if I have like little o of n average degree, I can still get a sublinear sample complexity as long as there's enough edges. Yes, this is not true actually for many bounds in this area. They often have some hidden exponential. But for us, we can gracefully degrade, which means we can get sublinear sample complexity for many Ising models, even though it's impossible to get constant sample complexity for them. And OK, so that was just a sort of information theoretic maybe result. But because computing the free energy of the small guy, that could still be hard. But there's a few cases where it's actually easy, right? So if the small guy is ferromagnetic, so if the original graph is ferromagnetic, of course, then you can approximate the free energy very, very efficiently using this famous Jerome-Sinclair algorithm. And the point is that actually that algorithm has a very bad dependence on the size of the graph. So it's a polynomial, but a very high degree polynomial. So it's very interesting, I think, that we can completely eliminate the dependence on n. So it's like n to the 11th. Yeah, at least that's the best upper bound we know. And so this still applies. When the average degree is high enough, we can get this accelerated algorithm where you just sample a small subgraph and then compute the free energy using the Markov chain method on that model. And as a technical result for KMRFs, this is the only way I know how to get sort of the correct answer, which is that you should be able to approximate the free energy in time 2 to the 1 over epsilon squared. So you can't just use the sampling result, but combined with some other facts using regularity, you can get this. And yeah, I really don't know any other way to get the correct answer, or what I think is the correct answer for this. OK, how much time do I have? Oh, 3 minutes. Wow, I have a lot of time. OK, so yeah, so basically all of these kinds of problems, there's some way in which they're all the same. So what do I mean by that? Well, OK, first of all, we know everything about mean field approximation. So we'll just apply that. I mean, our graphs are dense. But that doesn't really solve the problem, because now I need to compare these two optimization problems. And they're on different sets of variables. And they have, one of them is a random optimization. So it's really not like a trivial thing to control. But there is actually one part which is trivial. So I've got the top guy is the free energy for the big model, and the little guy is for the small model. And if I have a good solution for the big model, well, I can just restrict that to the small model. And we know concentration inequalities. So it's going to be a good solution for the variational problem in the small model. So that means when I sample down, I'll always get a free energy which is at least as big as what I expect. But then the hard thing is, OK, well, there could be a product distribution that sort of exists for the small model, which is unexpectedly good and sort of doesn't generalize to anything in the big model. And it's not that easy to control this kind of thing, right? Because one thing you could try to do is just, there's only so many product distributions for the big model, and I try to control them by a union bound. But basically, this n is infinity, so this is an infinite union bound. It's not going to work. I can't talk that much about the proof. Well, OK, I'll give a proof sketch, very high level. Basically, the first trick is use weak regularity, and it lets you write things as convex programs. And then the magic is going to happen when you actually study these convex programs. You'll find that they have a really nice dual certificates. Actually, there's still some more complicated stuff because the dual certificate could be unbounded. So there's some trickery involved here. And it actually seems like a small miracle that the dual certificate has the right property. But yeah, it works out when you compute it. OK, so this is an open problem I would like to share. So I think it's very interesting. So if the optimal sample complexity were 1 over epsilon squared, it would be really nice, because that would mean if I want to compute the free energy of a big Ising model, there's not, we know of very complicated ways to do this, but there's a very simple way, which is just to sample down to this small model and then brute force compute the free energy. And you kind of think that maybe this would encode all of the tricks that we're using in these more complicated schemes. But unfortunately, we don't even know that that would work for maxcut. So I think this is the #1 open problem here. And of course, if you can prove a lower bound, that's also interesting. But I don't know if we can do it with the current techniques. So yeah, it may require some genuinely new idea. Yeah, that's all I wanted to say.
Any questions for Frederic? Yes, no? Speak up, because I can't exactly see you. All right, so no questions. Thanks. So